Almost 2 years, 3 years.
Alright, guys. This workshop was actually supposed to aim at audio signals specifically, and I just now shared two kernels, Kaggle kernels. You can just, I don't know, like start it on your systems if you have them. If not, then I'll be anyway going through them here. Okay, the projector. All right. So the thing is, does anyone know about speaker diarization? Anyone? So what speaker diarization is, given a clip, you will be able to segregate between speakers. Okay. There are many techniques for doing it, and it is kind of an active like area of research right now. Google is actively working on it. But then again, there are some trivial approaches, and what these trivial approaches reveal are the set of features that you should be looking at while working with audio data. So this is what exactly the talk is focused on. So let me just find that clip so that I can play it. Can you hear it?
No. Yes. I get it.
Oh, yeah.
So the clip is from a movie called Lost in Translation. The two people talking are, any guesses? Scarlett and Bill. Absolutely right. So this was an interesting clip for me, so I thought of applying speaker diarization on this. So this was exactly the reason why I thought of presenting this. Okay. So the first part of this talk will be about understanding how clustering works. Why exactly do we need clustering? Good question. So technically, we are trying to cluster the audio data in 2 or 3 segments based on the speaker. Like we are hoping that the data gets clustered among speakers. So first speaker will have a cluster in which all the audio samples that belong to that particular speaker will be clustered into, and so on for the other speakers. So this is speaker diarization. This is the layman definition for it. So you have speaker A, speaker B, speaker C, and silence and so on, getting segregated, just in case to avoid jargons. So we have many viable options for clustering algorithms. Kmeans is by far the most well-known of them. It has its pros and cons, which we'll encounter when we actually work with this. Then we have affinity propagation, mean shift, dB scan. dB scan is something I worked with while outlier detection. It's computationally very intensive, and there are many more. The list and which one works on which kind of data can be found on scikit-learn. So let's see what we have in Kmeans. People who know how Kmeans works. Come on, guys. Kmeans. Okay. So say we have a sample space 2D, and like it appears that we have two clusters. Like visually, we can make out that there are two clusters, but how exactly would you ask a computer to segregate them? By just giving it a parameter k equal to 2 and asking it to label all the samples based on some sort of features that you have defined. So in the way this works is initially k means just sprinkles two centroids at random. So let's say these are the two centroids, and the next few steps are repeated for a few number of iterations. So the step is you find the distance for each point from the two centroids and compare them. So say the red distance is lesser as compared to the green one. So this particular data set gets the red label. Similarly, for another data point, this one gets a green. And similarly, all the points are labeled. An interesting thing to note is, let's say, in a rare occasion, somehow a point in the left-hand cluster has a red label. Like by chance you got the red centroid closer to it, but like in the end result, you wouldn't be expecting that. So the next step the algorithm takes is calculates the centroids again, and this is done by like the name suggests centroid means. So you find the mean. Now just because that red sample is there, that's why our mean for the red cluster is not exactly like where we would have expected it to be seen. But remember, this step is being repeated. So next time when we have this labeling done again, like this will be done again. The thing where we compare the distance, you will see that that particular sample will automatically be included in the green cluster. So that is how the K-means algorithm works. And for the code, as we are not coding, I'll just like skim through this. We are using TensorFlow, Pandas, NumPy. If you're working in Kaggle and if you want, okay, this is pretty trivial. I'm creating dummy data, and this is the dummy data in 2D space. So it's visually clear that we have 4 clusters. So like it won't be feasible for you all the time to decide how many clusters you have to pick, like k equal to 4 or 5. You won't be knowing that. Like for our case, we know that there are 2 speakers, so it would be a good guess for you to take k equal to 2. But that might not be the case for all the time. Let's say you are clustering newspaper articles and you don't know what kind of headlines you might get. So in that case, there's something called the elbow rule, which I'm not very familiar with, but I read it somewhere back in my college days. So going forward, you have K-means utility functions, assign centroids, recalculate centroids, written in TensorFlow, written using TensorFlow APIs. And you have the main driver function. Here I have set k is equal to 4 because I know there are 4 clusters. And epochs is number of iterations, that is 10k. You can have it tuned down to 5k, 4k depending on, it totally depends on how quickly the algorithm is converging. So as you can see, our algorithm did not perform quite well. So we have the red dots as the final output. And you can see that there are 2 centroids that have somehow converged to the same cluster. So any guesses why this might have happened?
That would be closer to that.
Sorry?
That would be closer to that cluster only.
No. I mean, technically yes, but at some point in our algorithm we went wrong with something. And that is why this happened.
initialization of centroid.
Exactly. So while initializing, we are randomly scattering the centroids at the beginning of the algorithm. So if somehow you scatter the centroids in one cluster, or let's say you have put them in such an awkward position that they will end up converging into the same cluster. In that case, you are not guaranteed to have a good result out of k-means. So this is one case where k-means fails badly. So this is when the scope for improvement in k-means came in, and this is known as Kmeans Plus. In this case, the algorithm is pretty much the same. The only improvement is in the initialization step itself. So here we have three visibly like separable clusters, and in the first step we pick a point to be our centroid. So let's put this technique to a good test, and we have selected a point which is kind of fairly in the middle of the dataset. So the next step is to find the distance from your currently selected centroid, and you will have to find the distance from all the samples to your currently selected centroid. So in that case, and the point which will have the maximum distance will be selected as the next centroid. Any guess why we are doing this?
Cover the maximum range to separate the most separable, most far apart clusters.
Yes, because we want to scatter the clusters in such a way that they don't end up in the same cluster, right? So if by chance our first point was indeed in a cluster, this technique guarantees that the next centroid that we are picking for initialization won't be in the same cluster. So for distance calculation, we are using Euclidean distance, and using that we end up there with our second cluster. Now the technique suggests that it's the same thing, finding the distance from all the centroids that you have picked, the furthest will be selected as the next centroid. So that, and now whatever you do, you will end up with good clusters.
But in this case, it could have been that again a centroid got selected in the previous cluster towards the end.
But you are comparing it with the two previously selected ones, right? So this is how the.
Can you do me a favor? Just put all your slides and the Kaggle walkthrough that you had on Telegram channel, so people who want to follow and can try it out at the same time.
The Kaggle kernels are there on the Telegram group. I just posted them. Okay. So with that, we'll get back to coding it on our kernel. So this is the improvement. This is straight away copied from Geeks for Geeks, so don't judge me. Minor improvements here and there. And you end up with something like this. So this is Kmeans Plus selecting its first centroid. This is selecting the second one. This is selecting the third one. This is selecting the fourth one. So our initialization is already at a great start. And then it's pretty much trivial k-means, and you end up with good clusters. No matter how wrong you can go with k-means, you'll always end with good clusters. This dramatically reduces the number of computations you'll need with the actual steps of k-means, even though it increases the initialization time, but at the end you are guaranteed to get good clusters. Not exactly guaranteed, but the chances of you going wrong is reduced by a great number. Alright, so this was the basics of clustering that we will be using. There are many sophisticated clustering algorithms that you can use, but being a walkthrough, so I kept it simple. So this is going to be a bit interesting, depending on if you're actually interested in this. Okay, so before we actually, in the previous code, we were generating our own sample data, dummy data rather. It was a 2D feature space, which means that each point is represented with x and y, x1 or x1, x2 if you prefer. But that again can be extended to n dimensions. Your feature space can be of n dimensions, right? So then again, if you know what feature engineering is, they specifically work on this, finding the right features for your model. So if you say you have a cup and you have a bottle, so if you're training a model and it is supposed to classify the two, and you want to know, you give the model a picture and the model tells you which one is a bottle and which one is a cup. So to begin with, if you just randomly pick a feature, let's say if it is a cylinder, then maybe that is a feature. Okay, cylinder, yes or no, this is a feature. So in that case, it is not doing us any favor, right? Because both are cylindrical, kind of, right? So then you pick another feature, ceramic, plastic, but then again, plastic cups are there. Then what else? Open from the top, maybe that is a good feature. So this way you keep on increasing the feature, and the way to visualize this is, if you have a 2D space and you have like samples that are kind of overlapping, and you add one more dimension and you lift the whole thing up, and they somehow get segregated. If you squash them back, they are again, overlapping, but if you like pull them apart, they are segregated. So this is how visualization might help when adding feature is a good thing sometimes, but then again, you are adding to the computation, so you cannot just randomly add features, like adding thousands of features and expecting your model to be trained within a day or two, right? So in our case, it is audio data. So let's say, basic question, what is audio? What is audio? Sorry?
Frequency.
It's changing frequency.
Frequency.
Is it frequency?
It's changing
Frequency
frequency.
and time. Amplitude. You got volume of. It's got different frequencies and different volumes.
Pressure variations.
Getting closer?
Pressure variations in air only.
Medium.
In a medium, yeah. Pressure
Okay.
variations in a medium,
So pressure variations in a medium over a period of time,
which is audible.
which is audible depending on the frequency. So this is what sound is. Change in amplitude over a period of time. How fast that amplitude changes from one value to another is frequency. So this is inherently a part of the data. This is not a separate parameter. This will be easier to visualize in the next slide. So this is your sine wave. You have amplitude varying over a period of time, and this is one full cycle, that is your time period. And this is a 440 hertz. People who are from music background, you know what A chord is, right?
Yeah.
A or ni in Hindi.
Right.
So this is what ni sounds like if it is actually a sine wave. Not sure if that was audible, but it is very audible. Okay. So so practically everything that can be a wave is sound. Okay. Like given that it is within 20 to 20k hertz, that will be audible. But any wave that you can visualize will be sound. Okay. So before going deeper into that, let's see how we actually have that on our computers, like how sound files are actually stored on our systems. So again, back to our sine waves. So in computers, as we know, there is nothing called analog. Everything is digital, right? So there are bits. So you cannot have continuous values. So your amplitude will be broken down into bits. So your files will have something called bit depth. Audio files have something called bit depth, which defines what kind of resolution you will have when you're talking about amplitude. So in our case, we have, let's say, 9. Yeah. So in that case, our amplitude can take 1 out of 9 possible values. So then again, the time is continuous in this case. So that is again not possible. So we'll have to break it down again. So we break the whole signal over the whole, like let's say taking a song into consideration. A 3-minute song will be broken down into regular sized samples. So there you have samples. So each sample will have a particular bit depth, as in like a particular bit value, and if you put them together, you have the song. Okay. So what's the resolution of your song will be defined by your sampling rate rather. So if you have a higher sampling rate, you'll be capturing more number of samples within a second. If you have a lower sampling rate, you'll have coarser version. So back to our kernel. So in this case, there are a few things that you might have to do while dealing with audio. Firstly, you'll need ffmpeg for running librosa. Librosa is the library we are using to deal with audio. So this is how you install things on Kaggle kernel. If you want to install anything from the aptitude package manager, this is how you do it. And other than that, Seaborn is a good library for visualization. Then blah blah blah. Okay. So this is the very audio file that I played at the starting of the workshop, and here we have a sampling rate of 22k, and these are the number of samples we have. So this is kind of an array, not kind of, it is actually an array, which has some value at each index, and that is basically the amplitude at that particular sample value. So if you want to verify whether this is indeed what you extracted, you can play around with the sampling rate and the number of samples you have, and you actually get back the exact time of the song. That will give you an surety that, okay, this is indeed the whole song that we captured. All right. So that was the song. You can play it again if you want. It's a nice little dialogue between the two actors. And then this is the waveform of the whole song. Sorry, the clip. So waveform is basically amplitude varying over time. This is the time domain vision that you get that Sir was talking about. So from this you won't be able to make out much because this is just amplitude variation. So this is more like, okay, someone is speaking louder maybe, like on a rough scale. But if you go down into details, this is actually the wave that you will be analyzing on. So whoops. All right. So before going deeper into this, I'll get back to my slides because this will need a bit of theory. So amplitude done, total time of the song is known, that is done. So how do we extract the frequencies? Again, so I already explained how we do that. We use Fourier transform. So Fourier transform, the theory is every wave can be represented as a combination of multiple sinusoidal waves, sine or cos waves. And like some clever engineers came up with like converting it into Euler function as well, so that makes it easier. But all in all, you can pretty much convert any wave into combination of sine waves. So that is the gist of Fourier transform, and this is how the two domains would look like if you were looking at them simultaneously. So from time domain, you have the time axis and the amplitude going up and down. So the amplitude, this is a 3D diagram. I hope my drawing is apt for the occasion. So this is a sine wave, decently sine wave. So so the amplitude is going up and down, and if you were looking from the time domain, you will just observe the the amplitude going up and down along the time axis, right? Now, if you apply Fourier transform, you will be taking a look at the wave from frequency domain. So the time information is lost, yes. And in this case, it doesn't make sense doing a Fourier transform because it was a pure sine wave. You will get back the sine wave. So you will just get the frequency value of that sine wave. But any wave can be converted into a combination of sine waves or cos waves. So let's say you have a very complex signal and you convert it and you get a combination of sine waves. So this is how it will look. So you have multiple sine waves and you will get a plot of different frequencies in the frequency domain. Any doubts so far? So no doubts, so I get to ask. Alright. So we know the concept of pitch. It is somewhat related to frequency, I guess.
Yeah.
People who agree, show of hands. So if I play a guitar string that is labeled as A, and if I play a piano key labeled as A, both in the same octave, why do they sound different?
Because of something called timbre. So you have, an instrument note is a combination of multiple frequencies, or it's like harmonics and all, right? So it's not
Correct.
a single wave.
Correct, you're ruining my talk. Okay.
I'm not even an engineer, I just know this because
That's actually like very correct. This is what we studied back in our 12th grade and I did not even pay attention to what it was. So classic education system. So this is what we call timbre, not timber, spelled as timber, but timbre. And what timbre is basically is every sound has a fundamental frequency. So that is the most prominent frequency and possibly the highest valued frequency. Not the highest value. It's, how should I say, the frequency which has the lowest value. Getting it? 440. That's A. Okay. Anything over that will be least significant, and 440 will be considered your fundamental frequency. So any note that sounds like A will have 440 in it, which will be its prominent frequency, and that will be referred as the fundamental frequency. But a singer singing A as compared to a guitar string strung playing A sounds different because of different harmonics that it generates. So this is our fundamental frequency. These are the overtones. Overtones are anything that have a higher frequency than your fundamental frequency. What harmonics is, they will be multiples of your fundamental frequency. So in this case, it's pretty evident.
Yeah.
So theoretically, you can have infinite number of harmonics, theoretically speaking. But in actual, like in real life, what happens is each particular instrument, or like our instrument is our vocal tract. and everyone's vocal tract is designed differently, and so are different instruments. So they have a tendency to suppress a particular harmonic and like favor a different harmonic. Okay, so these combinations of different harmonic is what gives that instrument a unique sound. If you're able to mimic exactly all the harmonics that instrument is generating, you'll be able to replicate it completely. And this is the reason why two guitars sound different, even though you're playing the same string, because the wood is different. The wood has the tendency to suppress one harmonic as compared to the other. So before I play this is very cool. Okay. So ideally, what you might be thinking is when I pluck a string, it like goes back and forth. But that would have happened if the string would have started from an actual bow-like shape and you left it from there. But when you actually pull something, it is not in a bow-like shape. It is like a triangle. You agree with that, right? So this is why we have irregular waves being formed at the string, and this is why there are many superimposed waves being generated from the same string. But the string is tied at two ends, its length is fixed, its girth is fixed, so it can only vibrate at its natural frequency. Yes, that is, let's say, the A string, 440 hertz, but it will also be able to vibrate at multiples of that, right? So if you look at this, okay, kudos Airtel. This is a slow motion video of a violin string being played. So you can already see that it is not having uniform vibrations. Cool, right? So this is what gives rise to harmonics, and this is the reason we have those complex waves as compared to sine waves. So if everything were a sine wave of different frequencies, will practically sound the same. Okay, so applying that to our data that we have captured from our audio clip. So what do you expect to see when we actually put this theory to use when we are analyzing Bill's voice as compared to Scarlett's?
Different harmonics for both of them, different harmonic combinations.
Yes, and what do men's voice and women's voice? Exactly, pitch. So the fundamental frequency will definitely be different. And Scarlett has a very nice voice, so when we, okay, one more thing. So, sir talked about something called short-time Fourier transform, STFT. So, on a practical level, if you apply Fourier transform on a complete 1 minute song, that won't make sense because you would just get all the combinations and there's no information as to when that frequency was there in the song, The song is made up of many frequencies, yes. So what we do is we break the whole thing into small chunks and we apply Fourier transform on that. So, and then actually what they are called is periodograms. So you have frequency values at that particular time interval. So if you shrink the time interval too much, you lose frequency information. If you increase a lot of time interval, you are losing at some other end. So you have to find a reasonable trade-off at what resolution you want to work with. So I pretty much went with defaults, and then again, when you have this information and you stack them like side by side back again, what you have is something we call the spectrogram. So in this, you can actually visualize the time and frequency data at the same time. Time, frequency, and amplitude, rather. So this is what it is. And applying log on this. The reason why we chose log scale is because if you observe, okay, this is too tiny. Most of the action is going on here. You can see the harmonics going up, but most of the stuff is going here, so we are applying log. So log scale will let you visualize things on the lower end more clearly. So applying log scale, and now you can see a lot of things going on in the audio clip. This is the audio clip from 0 to 1 minute 10 seconds. And you can pretty much differentiate between the speakers by just looking at it. So you see that 256 there? You guys can see 256? No? You can see my pointer? So here, you see this is the lowest frequency that this particular region has. Similar case here, similar here, here, and so on. And these particular samples, should not say samples. These particular frames have frequencies that are much lower. So on a rough guess, this is Bill speaking, and this is Scarlett speaking. Just a guess. And then again, the spectrogram also gives you amplitude information. So this is kind of a heat map. So the brighter the color is, the more dominant that frequency is. And as you can see, there are multiple overtones. So the concept of overtone can be visualized here as well. So if you were to segregate between two male speakers, this can be a very crucial thing to note. All right. So now that we are done with the basic theory, we can start thinking about which features to actually extract from the audio data. So there has been a lot of research done on this topic, like which particular feature is more relevant as compared to the others when it comes to audio data. And as it turns out, audio data is harder to work on as compared to image data. And many people have tried working with CNN and applying it on spectrograms. That did not end well because image is like if you turn it around by 90 degrees, it is still the same thing, right? But spectrogram, if you turn it around, the axis is changed, right? So there are a lot of things going on, but like it is an interesting thing to work in. So there are a few features that I looked up, and again, this was done in a 15-day span, so don't grill me on this. MFCC is Mel Frequency Cepstral Coefficient. Mouthful name, but the gist of it, this thing is, once you have a Fourier transform, we apply a few more transformations on that. Actually, an inverse Fourier, but before applying the Fourier, we actually take a log. So while applying the inverse, we are not actually going back to the time domain. We are going into a domain which is referred to as Q frequency domain. And what MFCC actually gives you is a set of coefficients, a set of 40 coefficients or more depending on how you set the parameters for this. So the first 2 to 13 coefficients will give you the spectral envelope. This again is a very like big topic to talk about, but all in all, this particular feature is single-handedly used for speech detection. So this is how important this is. So the first 2 to 13 coefficients are used for giving you a spectral envelope, and the theory behind this is spectral envelope is basically a representation of your vocal tract. So if you can figure out the spectral envelope, you can pretty much figure out what the speaker was speaking. So this can be mapped to a word. This is the gist behind this. But the rest of the coefficients will give you other finer details like the overtones, which are usually ignored when you are working with speech detection, because if you were to recognize a particular word, it should not differentiate between a man or a woman, right? So the first 2 to 13 will completely ignore the overtones and all those minor details, but the rest of the coefficients will have that information. So while using this particular feature, I actually like took all the 40 coefficients that I could use. Then we have spectral centroid. This is basically a weighted mean of the frequency that are there. Then we have spectral roll off, which is basically the frequency bin under which 85% of the energy of the whole wave is lying. And then we have zero crossing rate. So a wave goes from positive to negative times and again. Zero crossing rate is basically what it says. This is majorly used for detecting percussion sounds. So the more number of times a sound crosses zero, the higher the frequency might be. This is kind of the gist of the feature, and this definitely deserves its own talk. So we won't be going into much detail. I wanted to, but then again, like I have a habit of keeping things short. So okay, so back to the code. So I have created. Okay, here I've written 4, but I'm actually taking chunk sizes of 0.125 seconds, and each chunk will have 2.7k samples roughly, and then I'll extract these set of features from these samples. So basically, all those set of chunks. So there are two things going on. Firstly, you are going to do a speaker diarization, right? So what you want to do is create chunks from the whole timeline. You will be labeling those chunks to a particular cluster. Now, on each of those chunks, you are going to extract the relevant features that you think are necessary. So 560 is the total number of, 560 is basically representing your whole timeline. So you have 560 samples now. K-means will be applied on this 560 samples. 40 in our case is the coefficient that I was talking about, and Librosa generates 6 per coefficient, so we'll basically take the mean to simplify things. Similarly, for spectral roll-off, you have 560 and 1 in this case. Centroid, same, and zero crossing rate. And then you basically take the mean so that you can simplify things a bit, and you stack them up in a nice little matrix using pandas. So you can visualize this. I have displayed the first 5 samples. So you have MFCC values all the way to 40, and then you have spec roll-off, spec centroid, ZRC for each sample. And there are 560 of them. I just displayed 5. So now that you're done with this, you basically copy paste the whole thing from our last kernel, and you end up with this. You run this code, and you get this nice set of labelings, and these are in order of the time they happened in. So here you can get a bit creative for visualization process. So I wrote this little function, frame condenser and rectangular generator. This is basically playing around with things like you have 2 labels simultaneously, so you pack them up together and keep a record of how many frames you caught in that, so that you can get a rough guess of how long the rectangle should be to color code the whole audio frame. So all in all, when you run this, you get something like this. And again, like this is a repeated question, why k equal to 3 and why not k equal to 2? Repeated question, come on, easy. There are 2 speakers, right? Why k equal to, exactly. So as you can see, the red region is basically representing the zones where the speakers have kept mum, and this is Bill speaking that I know. So blue, this is Bill speaking. Yeah, I've heard the clip, so I pretty much know that it is doing a decent job. But for some reason, it is more or less missing out on Scarlett's voice. So you can play around with this kernel and see what you can do with it. So this again, like okay, this has a list of all the resources that I combed through to prepare the slides and all. So you can just visit them one by one. So it's pretty interesting. So like we were expecting very clear clusters, but actually, okay, this was supposed to be more dramatic, but we are not doing a hands-on, so this was very anticlimactic. So never mind. So we did not get a good set of clusters or a well differentiated set of clusters. So why did that happen? So this is where understanding the data becomes important, and picking the right algorithm for it becomes important. So K-means has a very specific definition that it will work on Gaussian distribution. I mean the data sets which are distributed using Gaussian distribution. So Gaussian is basically if you just visualize a point around which all the data is scattered around, like a big ball of data. So you have a ball of data here, you have a ball of data here. Easy. You put a cluster here, you put a cluster here. But what if your data looks like a hull? You know what a hull is, right? Not the Hindi wala hull.
Ship's hull.
Yes, ship's hull. Hull, like the ship's hull comes from a different hull. So hull is basically you can something wrapping something. So if one data is wrapping another data, in that case, K-means will fail badly, because if it picks one point as centroid, it will automatically consume the hull as well. So in that case, you won't be able to segregate the data. No matter how many dimensions you add, you won't be able to separate them as well. So in that case, there are other algorithms that perform well, like dbScan is one of them. So then again, there are other problems with K-means as well, like if there is improper distribution, as in like one cluster has a lot of data as compared to the other having a very like small amount. In that case, also it does not perform well. It is very sensitive to scaling as well. So these are a few of the things that K-means is not so good at. And then again, I was listening to a talk by a researcher from Google. So he is currently working on speaker diarization, and he actually told in his talk that audio data is not actually Gaussian as we might expect it to be. So they came up with very interesting ideas. Like they actually made the data into Gaussian and applied Kmeans Plus Plus. So that is another dimension of research that you guys can look into, like converting the data space into something else and like deploying a very simple algorithm like K-means, right? So that is also included in the last kernel that I shared, so you guys can check that out. And yeah,